All right. And I am putting the, see, there was some trouble with it, so I am posting them to YouTube. Every once in a while, this program gets a little. So today, yep, Rudy, I just turned it on if you didn't see it. Let me double check though. Yep, I'm recording. But thanks for the reminder. So today, we're going to talk about convolution, which can be considered, like a dreaded topic of EE. But I spent a lot of time investigating on how to teach convolution, and I don't think it really has to be that bad. All right. And really, what we're doing is we're going to take a signal, and that's usually called something G of T, right? And we're going to input it into a system usually called H of T. And we get an output of time. Now, mathematically, right, and we're going to call that function of time f of t. So if we write this mathematically, we're going to have our new function of t, our signal, and this is the convolution symbol. Right? And then the system, which is a function of time. All right. Now, just some things. These are all linear operations. All right. And it doesn't matter which order these come in. And in fact, we're going to find that some signals can also describe systems. All right. And vice versa. All right. And then on Wednesday, we're actually going to do this a different way in the frequency domain, and we're going to use something called the Laplace transform. All right. Now, what does that symbol mean? All right. Well, it is an integral, and it starts at minus infinity, right? And it goes up to t. In our previous examples, we had these limits, right? But now this isn't a constant, it's actually a function of t. And what that means is we can't use that as our integration variable. So we switch to tau. Even though tau can mean RC in an RC circuit, in this case, it's what we would call a dummy variable. Right, now we have the multiply symbol, we have h, and then we have t minus tau. All right, d tau. And this can get kind of complicated. But if you look at the notes or the prepping for class, if you don't quite remember what I say, you can go back there and read it. But the book kind of shows it in the most complicated way possible. But really, there's a procedure, right? Just trying to move that a little bit. That can take, that can allow you to really simplify things. And so they have a lot of rules about dealing with delays and things like that, but really, right? You break the whole thing up into simple, right? Right. And I think we're going to circle back to this later, and it'll be better now to do these simple functions so that then when we do more complicated linear sums of these, then you'll see what we mean. Now, in all of these problems, you do have to plot out the function, all right? And this actually seems to be where most people have a hard time. Doing the manipulation, people seem to get the answer right, but then people get some weird plots, all right? Okay, but we'll get to weird plots later. So on a previous homework, right, we were doing integrating a delta function, but we're able to keep everything in time because we have these finite limits, right? And we know the area of a delta function given those limits is equal to 1. All right. Now, how is this different for when we're going to be convolving things is I'm going to take a step back and let's just find not the convolution, but we're going to integrate a delta function over time. Because we have time, we have to use t. All right. So let's so part of the definition of the delta function is that the area equals 1. All right. So you can think, right, we want a function of time. We're integrating with this dummy variable, but as we are finding the area, right? And now, just so you know, what I'm doing is kind of an intuitive explanation. So there's no delta function, so there's nothing to integrate. So the area is 0. But then right at 0,
Professor,
right, yes,
is the f of t equals the integral or f of t times the integral? Thank you.
sorry. Thanks for saying that. As it comes along, right, and then the integrator operation goes over the delta function, right, the area is 1, but then the area, there's nothing to subtract the area, so it never goes back down, right? So what we're getting is now the step function, okay? And then in a similar fashion, another f of t, right, we're going to integrate again, we're not doing convolution just yet. We're just integrating things in time. So we're integrating, and now you're just going to see me, well, there we have some area, then we have some more area, we have some more area, and if I had even steps, the area would increase linearly with time, and we would have the ramp. All right. Now, we can actually break this up a little. We can do this more mathematically rather than just say the delta function is an area of 1, right? Is that for tau less than 0, u tau equals 0. So that means we can set the limit to 0, right? And in this range from 0 to t, for tau greater than or equal to 0, excuse me, tau, u of tau equals 1. So I can just substitute 1 here, right? D tau, which would give me tau 0 to t equals t. Now I called it ramp t over here, right? Where did this step function go, right? Because here's the thing, it's actually right here. When we set that lower bound of 0, that means f of t is equal to 0 prior to that, all right? And so then we have t, but we just have to remember where it originally came from. And so we put back the ut, which then we get r of t. Okay. Now, when I say scale, I just mean we're multiplying everything. We're okay. Hey, Harpreet, kind of went over that before, all right? But for those of you who might need a little review, is a convolution is a mathematical operation that finds out what the output is when you input a signal into a system. Okay. And I'll leave it at that. So scaling, right, that's just a linear operation. And so if I were doing this, right, well, I know that this is going to give me UT, and then I just have to multiply by A, right? So that's when I say scale, right? And when we came back here, I said break things up into simple convolutions, right? Scale and delay, all right? That's the scale part. We're going to talk about the delay in a moment, all right? So let's redo the ramp function, but let's delay it. Let's find the integration though, but this time u tau, and we'll just pick a number 1.
But that was supposed to be T, not tau. Wait.
Yeah.
No, wait. No, wait. It's supposed to be U T minus 1, not tau minus 1. Isn't it?
Okay. So this is important. So I'm going to take some time, right? Is that when we had our finite limits, right? A to B, right? We could integrate with respect to T and come up with some answer, right? But now we have T we're coming up with a function of T, so we have to use a dummy variable, tau. Oh, I'm not doing a convolution yet. Maybe that's your thing?
I don't know. No, I thought.
This is the dummy variable, tau.
Yeah, okay. I understand
Okay.
that. I understand that.
Okay, yeah, no, I hadn't. All right, okay. All right. Now, the thing is this one's actually not that hard to do because this will be for tau less than 1, it's going to be 0, and tau greater than or equal to 1, it'll equal 1. And so you could very easily do this and come up with the right function, all right? But that is actually too complicated. It's too much. What'll happen is that when you start doing multiple delays, it gets too hard to keep track of, especially with the convolution integral. All right. So really, the way to do this is do the integral without the delay. What do I mean by dummy variable? All right, a little aside here, dummy variable. We're coming up with a function of t, right? And so mathematically, right, we can't we can't integrate with respect to t when we're finding a t. So mathematically, we use a dummy variable that we're going to integrate over that's on the same axis as t, right? So that mathematically it makes sense. Now, sure, you could do it with t, right, and go through the steps, but it would be even though you could come up with the right answer, it would be mathematically wrong, right? And yeah, Kevin's answer is a good one too. You guys can read it in the chat. So do the integral without delay, right? So that really means just do f of t, and now I'm going to do from 0 u tau d tau, which we already know equals ramp of t, right? Then put the delay back in, right? So this is RT, right? Then you get that. And this is shown much more clearly at the very end of the Laplace transform section. But it's really quite useful when we're doing all of this in the time domain. Okay? So why don't we do a convolution? Okay? So this is the convolution operation. Everything's in t, right? It's when we actually do the convolution integral, all right? Now, there's just an identity, right? That if you convolve anything with a delta function, you're going to get the original thing, all right? And so in this case, by an identity, I'm going to get, so I'm convolving a delta function with a delta function, so I'm going to get a delta function. However, right, I've delayed one of them by -1, so they really won't overlap until -1. There won't be anything to integrate. And so that's what I mean by delay it. So convolution of delta by delta is delta, and then I keep track of the delay, and I just put it in there. All right. How does that work? Maybe from more of an intuitive sense, is that that's at 0, right? And then this other, and when I write out the convolution integral, it'll make maybe a little more sense. Or actually, I'm gonna, is that we're moving one signal through the other, right? And so when we had a delta function at 0, and we're moving this other function through the delta function, there's no delay to it. So it just comes out delta t. But in order for this delta function to actually overlap, right, it takes 1 second. All right. Let's just do.
So is the first function the moving, and then the second
You
function
know, it.
is
In this
how do
case,
you know it's not?
in this case, right, that's delta t minus 1, right? And this one is just moving along, right? Now, I could keep this one at 0 and move this one along, but it's off by 1. It's just easier to see that way. All right. Now I'm just going to give you the answer, right? Because this should just sum the delays and give me delta 2. Delta. Delta
Is
2.
your is your blue function another function?
I'm sorry, I didn't quite get that.
Because from a delta t minus 1 should not equal to this.
Oh no, this is a different one now. Now I'm doing this. T plus 2, T minus 2. Okay. And you just sum these delays. You know that delta convoluted with delta is delta, right? And here, so delta convoluted with delta, delta, and then you sum these delays, and I have 2 and minus 2. And that sums out to 0. Okay. Now, how could that look? Is let's just take one of them and delay it by 2. But this other one is here. Now, yeah, it's minus, but that means it came two units early. So if this came 2 units late and this came 2 units early, it's going to end up right in the middle at 0. Okay.
How come in the previous one it didn't wind up at delta t minus 1/2? Because it would
Because I'm
between
summing, not
delta t
averaging.
and delta t minus 1.
I'm summing these times,
Okay.
not averaging. Good question, though. All right. Okay. So now let's convolve a step function with a delayed step function. All right. Now let's put this into the convolution integral. All right. And this bit might be confusing, right? And so some might actually rewrite it to take this part and put it here. And put the part with the dummy variable in there. Okay. The problem with that simplification is that what if they're both delayed? And then it gets a little bit tricky to keep a track of that. All right. And I used to spend a lot of time telling you how to deal with all the tricks of delays and things like that, when really all you need to do is find the simple function, which in this case is just ut convolve with ut. And then we're going to scale and delay it. All right. So let me change colors here. There's our convolution integral. This forces the function to be 0 before t equals 0 or tau equals 0, right? And basically, when there's something to integrate, both of these will be 1. All right. Which then gives us tau evaluated at z which is now t, right? Because of those original step functions, we put back, and then we can write RT. Okay. All right, those are great questions. And I'm just going to take a little aside to explain that. Is that this is shorthand for convolve. This is multiply. All right. Math, right? Programming right, you would need convolve g of t, h of t, right? And multiply in programming would be that symbol, all right? So when you're writing your lab reports, right, we have, this is modern days, we have an equation editor in Google Docs and in Word. And so really you can't just program your equations. You have to make them presentable, okay? So just right? We have g of t convolved with h of t. When we put that into the convolution integral, right, we have g of tau. And now we're back to the multiply symbol. Oops. Okay. All right. So coming back, we found the convolution integral, or we found the convolution of a step convolved with a step, right? And now let's just rewrite that. Step convolved with step equaled RT, right? And now that we have a delay, right? Well, really, this would be it in generically. You just sum those delays. So, for example, so UT convolved with UT minus 1, well, we sum the delays. 0 minus 1 is minus 1, and we get RT minus 1. Now let's plot that. Right. We remember that there's a step function in here, right? That's going to make everything 0. In this case, until minus 1. Now we get a slope of, that's our function there. We got a slope of plus 1. All right. Now, there can be some confusion around this, is that what if I want to break this back up into a step function, right? So while ut is RT, I have to put the delay in here to make it work out, right? And so I don't like to do it wrong, but let's do t ut minus 1, right? So it's going to be 0 up until minus 1, right? And then we're going to start multiplying by t. But t at 1 equals 1. And so what's going to happen is we're going to have a jump, right? And then we're going to have our slope of 1, all right? And in order to make this work, I'm just changing the scale to that's 0, all right? Otherwise, it wouldn't look right. All right, that's 0. And then it turns on, and then you have that discontinuity, all right? And that can play a little bit of havoc with your plots. All right. Mommy, can you turn that off? Okay. All right. So all right. Now it can help for us to plot things out a little bit before we get started.
So,
Oh, excuse me?
what does the mu symbol mean?
Listen, this is the step function. Sometimes I get writing very quickly and I use the mu, okay?
Okay.
Yeah, sorry about that. I do try. Mentioned it last time, but you know, it's all distracting. I'll do my best. Anyway, we have g of t. We have a step multiplied by 2 steps. All right. Let's. So I'm going to plot this one first. So I have a step, right? And this is 1 like forever, right? But then at 1, I'm subtracting 1. And so I come back down, right? And then it's 0 forever. Now, let's write this in the convolution integral, except I'm going to put h of t first, all right? So what this kind of has the effect of doing, right, is that for minus t along the dummy variable or the dummy axis, it flips this. And so what I get is a flipped step function that now I'm advancing, okay? And so it isn't until these 2 shapes overlap that we start to get any area, right? But what intuitively can see is that we should get, and now this is just like a kind of an intuitive plot, right? I'm moving this along, there's nothing. right? Then I start overlapping, right? And so I should get, right, as I do an increase in linear time, I'm getting a linear area, right? So this should be going up, right? And then,
I,
yes,
are you? So is the dark blue is our G of t, correct?
yes.
Isn't that a negative step function, or u of negative t?
No, that's over here. This is the rectangle.
Oh, I see. I'm getting my stuff mixed up. Okay,
No,
sorry about that.
no. This is the difficult part. So it's good to ask now. Um, so as this is sliding along, I'm increasing, but then it keeps going, but this area never changes, right? And so it'll flatten out, all right? So that's kind of my intuitive plot. That's what it should look like. I should, at some point, start to be linear. And then when the area no longer increases, because even though this is moving, it keeps moving, right? That's zero. So 1 times 0 is 0. So there's no area. Right here, right? It's 0 times 0, you're getting, or even this 1 times 0 is 0. It isn't until they overlap that you get some area. All right?
Professor?
So that's what you should get, right? Just for drawing it in an intuitive manner, right? But to actually do this convolution integral, right, this way, it's actually more trouble than it's worth. And yeah, you can break this up into u of tau times u of tau minus tau, and then find the subtracted and the delayed and then sum it together. And so essentially you multiply this through and come up with two separate integrals.
Professor?
Yes.
So for the G of t, you wrote u of t minus tau, right? I thought you were supposed to be
No,
u of t.
no, this is the convolution integral, and you put that t right there.
So you're not supposed to use dummy variables for that? Or-
That's a parameter that you put in. That's, you could think of it as having two variables. But no, this is the correct definition of the convolution integral. Okay? But notice I can, or you could think of it as a constant. All right? Because I'm integrating up to a constant. But I'm integrating with respect to tau, not t. So I can have t, right? I just can't, I can't have dt because we're coming up with a function of t.
Professor,
Yes.
does it matter how we write it because one of them is a signal and the other one's a system?
No, in fact, it's linear. So it doesn't matter which way. And the thing is, I mean, they're both step functions. So one happens to be a system and one happens to be the input. And if I didn't tell you which, you'd never know, but you'll get the same answer. These are good questions.
Another question. So for the G of t, why did you write it as ut minus tau instead of ut? Oh, yeah.
I didn't quite catch that.
So I'm a little confused about why you wrote u t minus tau.
Yeah.
Yeah, how did you come up with that?
Well, what I did is I actually switched things around. All right. So if you, I'm going to go to a different page. All right. So G of t convolve with H of t, right? I can put this or this will also equal and you can choose which way to do it because sometimes one way is easier than the other.
But how are you getting the t minus tau?
That's the definition of the convolution integral,
Okay.
okay? The reason why is that that's the function of t, and we're advancing it over here. And so it moves it along the axis, all right? But the minus tau, while we're integrating, flipped it, okay? And this is called the flip and drag method, and it can cause a fair amount of confusion. And really, it doesn't matter which one you flip and drag. You just do it to get an idea of what you're plotting. All right.
And when you say flip, you just mean with the respect to the y-axis?
Yeah. So what I'm saying is this is ut, right? This is u minus t. So I flipped it in time. So if you're saying the y-axis short, around the y-axis, yeah. Okay. That slide's got a little messy. So we can just do this algebraically and multiply ut through, all right? So we get ut convolved with ut, and then we get minus, right, ut convolved with ut minus 1, all right? Now, way back, I said find the common or find the simple convolution and then scale and delay, all right? So in this case, this is the simple one, all right? Because it's step convolved with step and there's no delay. Here, at the heart of it, it's still step convolved with step, except we're scaled by -1 and we're delayed by -1. And I don't have to show that kind of really complicated convolution integral because I can, now sometimes in my notes I call it ZT because it's like common or whatever. So I'll just come up with the common one, right? U tau multiplied U T minus tau. T, tau, which by now we already know is RT. Okay. So f of t is, here's our first one, and that's r of t, right? Now here's our second one. It's going to be some kind of RT. Well, we're going to scale it. Okay, scale it by -1. There's going to be a t in there. And now we sum the delays. 0 delay minus 1 is -1. All right. So what are the important times? Well, this is going to turn on at 0. This is going to turn on at 1. So these are like the times that I need to put, right? Well, now let's do it. The ramp function turns on at 0, right? And actually it keeps going on. And that's RT. This one, let's give it a nice red color. Turns on at 1. Oops. Okay. And we get this. The summation of that, right? 0 plus 0 is still 0. Then we're going up by 1. And then at 1, these two slopes cancel out. And that's what we ultimately get. And really, we just needed to know how to scale something by -1 and then sum delays to get what we needed. Okay.
Professor.
Yep.
So your previous example, was that the method of solving convoluted problem?
Yeah.
So like
In the time domain. Yeah.
so from my understanding is you have one function convoluted with another one. Basically, your second function, you're revolving it around the y-axis, right? And then time delaying it.
My pause is that you're kind of summarizing the flip and drag method,
Mm-hmm.
but it doesn't necessarily tell you like what's really going on. And okay, and it can really not make any sense. All right, so you have a system, right? and then you have a signal, right? But, you know, time goes forward. But no, we've got this thing where time is going forward, but somehow we reverse flipped it. And how the heck is that possible, right? Because let's say I have u minus t. Well, that means, you know, as time goes forward, I'm going backwards in time. At least it gave me a hard time with it, all right? Now, what's kind of really going on is that you're summing some echoes, really. And these are kind of my notes that sometimes I don't know if people really want to hear it or not, so I don't lead with it, all right? But convolution is a linear sum of the responses of a signal's echoes, all right, that are passed through the system, all right? And so if we have an infinite number of echoes, and again, some of these notes are notes to myself. They're not like ready for prime time, okay? So if you have an infinite sum of these echoes, right, it's continuous time, and we integrate in the time domain, right? But if you have a discrete number of echoes, well, then this actually is more like 112, all right? And you're doing convolution in discrete time. That's not what this course is about, all right? But if you start with, you know, discrete functions of time, and I'm integrating, right, here's my x of t times a delta function of t minus tau, right? I'm getting this, right? But now when I put it into a form of oh, that's not what I want. Okay. So here's the thing, is if I had like these discrete time steps, right? I have n 0, 1, 2, 3, and then tau n is minus 1, 0, 2 here, and then I have the step of that, right? Then I have this, and then I multiply them together. That's what I get. And then ultimately, I kind of get the sum of these things, which I think I'll do here. So what I was doing was I was convolving a step times a step, right? And then I added another step. And then I added another step, right? And I kept convolving these. Well, what I would get is a staircase pattern. Okay, it's 0, 1, 2, right? Well, what if instead of these constants, or like I had a delta t time step, here it's 1, but what if I let that step and delays go to the infinitely small, right? I'd have a delta t, right? So that means I would go up essentially I would become a linear function. Now with that delta t, you have to scale it, otherwise it would jump by 1 each time, all right? And so you would multiply it by that step. And so when you let that become continuous, then you get the ramp. But you are really just summing echoes infinitely. So you're not really, so physically, you're not flipping anything in time. It's just that convolution integral, right, kind of has all those delays end up flipping it when you're on the tau axis. and it can be helpful to try to draw what's going to happen. All right.
So I'm sorry, Professor.
Yeah.
So basically, it's like just to give us a picture of what's going on, but it's not necessary. You're saying it's more of just summing them up, I guess.
So what's really going on is it's an infinite sum of echoes, right? But when you're plotting it, that kind of flip and drag method can be useful for getting an intuitive sense of what's going to happen, right? So that you don't get the wrong plot. And what'll happen is, right, let's say and now I'm just going to draw the shape. Okay. So one of these stands still and one gets flipped, but it's symmetric, so it doesn't matter. So it moves along, right? And then it starts to overlap, right? And then it starts to not overlap, right? And in fact, what'll happen is it goes up, it reaches a peak, and then it goes back to zero. With the flip and drag method, you can get that it's supposed to do that shape. But what sometimes happens,
Right. And the
people will
slope
do
describes the area.
this kind of thing. And it really happens when you're doing ramp functions, where if I have, let's say I have RT squared, right? Well, that's really T squared UT, but if it's delayed, right, that's really T minus 1 squared UT minus 1, right? And you can, so you might have this kind of shape, right? And you're convolving that with a step function. So the area will increase, but you're integrating linear, so you're going to get quadratic, right? But then the area will slowly start, the increase in area slowly tapers off, right? And then stays the same, right? Now, if I do a rectangle, well, then the area does go back down. Sometimes people will do this crazy shape, okay? Now, that's more for next time. All right, I just wanted to do, okay. All right. Well, the thing is, right, at some point I start to do what you might call shortcuts, right? But let's just draw this out. All right, that's G of T convolve with H of T. All right, and we can, just like FOIL, right, multiply these all out, right? And so what we get is UT convolve with UT. We get minus UT minus 1 UT. We get minus UT. Oops, sorry, I'm forgetting my convolution symbols. And then we get plus ut minus 1 convolved with ut minus 2. All right, we've multiplied all of these through. At the heart of each one of these, right, is ut convolved with ut. Right, okay, this might be scaled by minus 1 and delayed by 1. This might be scaled by minus 1 and delayed by 2. And this might be scaled by plus 1, but it's delayed by 3, right? So again, we've done this one a lot. So the common function is ut convolved with ut, which is rt. All right, ramp function. And now we just have to scale and delay each one, right? So the first one, that's just r of t. The second one, it's going to be minus, right? And it's going to be delayed by 1 unit. This one's going to be scaled by minus 1 and delayed by 2 units. This one is scaled by plus 1 delayed by 3 units. All right. Now you can see that there's, on the time axis, we're going to have 0, something at 1, something at 2, oops, and something at 3. All right. So here's our ramp, right? Oops. The t minus tau is when I do the convolution integral. We've done this convolution a few times already today, so I'm not going to do it. I just know, I don't mean that in a bad way, but by now I know that it's RT. I don't have to do it out each time. Okay, good question. All right, so, but then at this point, I have a plus 1 slope, but I also have a minus 1 slope, so it flattens out. Oops. And then here, right, I have, the thing is this slope is, I still have a positive, right? I still have a minus. Right? So I've actually kind of at a neutral slope. And then I have a net slope of minus 1. Okay. So I had plus 1, then I had plus 1, minus 1, so it was flat. Then I had minus 1, right? Because these two would balance each other. And then at 3, I balance out that minus 1 with a plus 1. And I get a trapezoid. Now, if I want to know, you know, what value I'm at, I could substitute, you know, let's say at 1, right? T equaled 1, right? Well, at RT equals 1, I get 1, right? At R1 minus 1, I'm actually at 0. These are 0, these are 0. So that's how I know that I stop at 1. So next time, we're going to continue this conversation, but rather than use the convolution integral, we're going to use the Laplace transform, right? And then we're going to do more examples, right? We're actually going to do, you know, decaying exponential and things like that. On the homework, I let you choose however you want to do it, all right? And I think with the Laplace transform method, it's easier to see where that scale and delay comes from. So a lot of people choose to do it that way. Still, the plotting can get a bit tricky. So some kind of intuitive sense of where you're headed is good, all right? Because sometimes I'll have a complicated one that's a little bit too hard to do by eye. But as long as you get the shape right, then that's okay. Where, however, just so you know, for this kind of problem, if we're on an exam, no, you need to have these 3 points. It needs to go up to 1, and you know, but pretty much drawn just like I have it at a minimum. Some people, you know, of course, are better artists than I am. I know it's time for 112. And I guess with, you know, why don't you just email me any issues? And I did go through the Myopen math things. It seems to be working. I'm not quite sure what's been going on with that lately, but I know it can be frustrating. But I'll just leave it at that. Okay. All right. Have fun in 112.